Hello everyone. In this video, we will be solving the problem Unique Binary Search Trees 2. The problem statement is, given an integer n, return all structurally unique binary search trees which has exactly n nodes of unique values from 1 to n. If you look at example number 1, the given n is 3 and we need to return all the possible combination that we can build using 3 nodes. So if you look at this image, these are all the representation of the tree nodes that we can build. The first one is 1, then on the right we have 3 and then 2. The second one is 1 with a right leg of 2 and then a right leg of 3. There's one important thing that is mentioned in the problem. We have to build the binary search trees, which means that nodes needs to be built in such a way where the left leg contains all the value lower than the main node and the right leg will have all the values higher than the main node. If you look at these images, you will notice the same pattern. If I take this center one as an example, 2 is the main or the center node. On the left, we have 1 which is less than 2, and on the right, we have 3 which is greater than 2. Now let's switch to whiteboard and discuss the approach to solve this problem. To understand the problem, I will use the input as 4. To solve this problem, I am going to be breaking this into smaller problems and then solve those smaller problems first, which will automatically solve the whole problem. So here, instead of directly approaching all the numbers, cut it down into 4 sections. Let's start with 1. If I make 1 as my primary node or the main node, all the remaining nodes will be on the right side of node 1, 2, 3, 4. The reason being is none of these numbers are smaller than 1. So I cannot put it directly to the left leg. So the left leg will be null. And all of these nodes will go to the right. Just looking at the numbers 2, 3, and 4, if I were to build a tree node, I could do several combinations. I could make 2 as my primary node. I can make 3 as its right leg, and then 3 will have a right leg for 4. This is a valid combination. I can do something like this. 2 will have 4 as its right leg, and 4 will have a left leg for value 3. Right? This is a possible combination given I am using 2 as my main node. Now, if I try to do something for 3 as my main node, I can only have 2 on its left node and 4 on its right. This is a valid combination. Another valid combination is 3 will have a right node of 4, 4 will have a left node of 2. This is also a valid combination because we are not breaking the binary search tree rules. So we have already seen I can make 2 combination if I'm using 2 as my main node, 2 combination if I'm using 3 as my main node, and if I were to use 4, so this will look something like 4. 4's left leg will be 3 and 3's left leg will be 2, or I will have 4. 4 will have a left leg of 2 and then 2 will have a right leg of 3. Again, this gave me 2 combinations. So with 2, 3 and 4 as a right leg of 1, I was able to make 6 combinations only with this. As we do not have any numbers less than 1, the possible combinations that we can make with 1 as our parent node is 6. I hope you were able to understand how we broke it down into smaller subproblems and then solved it separately. Let's try to do another iteration with the same approach. Now that we have completed first iteration with the primary node as 1, let's try one with 2. So with 2 as my primary node, I can do multiple combinations. One combination will be I will have 1 on its left leg and the remaining numbers on the right, which is 3 comma 4, or I could do 2 with a left leg of null and right leg will have everything 1 comma 3 comma 4, right? Because that is also a valid pair. I can do something like 2 as my primary node. I can make the right leg as null, and on the left leg I can put all the remaining numbers 1 comma 3 comma 4. Please remember the reason why we are able to put a null on the right leg of 2 even though we have 3 and 4 is because we have a number which is smaller than 2 which we could use to build a newer combination. Earlier when we were doing it for 1, we had no number which was less than 1. All the numbers were greater, so we could not do a combination where we could put a node on the left side of 1. So these are the three combinations that I can build with 2 as my primary node. Now, just like the approach we took before, we need to solve these nodes, these combinations individually and find out how many pairs we can build. Let me try one as an example. So if I'm looking at this pair 2, on the left hand side it's only 1, so I cannot do any combination as such. But on the right hand side, because I have 2, I can do multiple combination. So 2 can have 3 as its right node and 3 can have 4 as its right node. That's one combination. The other combination is 2, left is 1, I can have 4 as its right leg and then 4 will have 3 as its left leg. So this is one combination that we can build. So for this setup, we can build two combinations. Similarly, let's try for this approach now. So with 2 as my primary, because I have null on the left, there's no combination involved there. But on the right hand side, we have 3 numbers. So we can do a bunch of things. The right leg of 2 should always be greater than itself. So I can have 3. 3 can have 1 on its left, 4 on its right. Or I could do 2, then it will have 4 as its right leg, and then 4 can have 3 on its left, and 3 will have 1 on its left. This is also a valid combination. Or let me see what else we can do. Yes, one more thing we could do is if I just open this part up, instead of having 3 and then 1 and 4, I can do something like 3, then 4, and then 4 will have a left leg for 1. That's also a fair and valid combination. So with this setup, we were able to find out 3 combinations. So now I will have 3 here. Similarly, if I try to go with this approach here, it will also get me 3 combinations. So my total result, so I will have 3 plus 3 plus 2, which is 8. 8 plus 6 is 14. So far, I have 14 combinations. Just like we did for 2, we need to do it for 3 and 4. Just to iterate once more, we solve this problem by breaking it into smaller sub-problems and solving individual nodes separately, and then at the end, adding the result together. Let me show you the C# implementation to solve this problem using the approach that we discussed just now. Here is the C# implementation. In the main method, I start with a validation to check if the input that is provided is not equals to 0. If it is equals to 0, then I return an empty list. Else, I call this DFS method, which requires a start and an end. If my start value is greater than the end value, I return an empty list. If that condition is not satisfied, we get into the main implementation where I have this loop running against all the numbers starting from 1 all the way to the end provided by the input, and separately we build the left nodes and the right nodes. If my start is 1, for example, all the left nodes that I could build will be collected in this left list variable, which in this case will be 0 because there are no nodes smaller than 1. And on the right list, I will have all the combinations or tree nodes that we could build with the remaining nodes. Once we have the left list and the right list built, then we iterate through all of those combinations like one at a time, like one combination of left against all the combinations of the right, and at the end, collect all the values or all the nodes and return them. In those combinations, we build a new tree node with left and right values and return the result. There is always a possibility that left is null or right is null, which still makes up a valid pair. After the iteration is complete, we return the result, which will have all the unique combination that we could build. I hope you were able to understand this solution and the approach that we took to solve it. If you have any questions or concerns, please feel free to reach out to me. I will be adding the link to the source code in the description below. You can check that out as well. And I will see you in the next video. Thank you.